Question 8.89 deals with the ideal gas law. It says nitrogen dioxide, so NO2, reacts with water to produce oxygen and ammonia. You can see down here we have a balanced equation. If a 5-liter sample of water gas reacts at a temperature of 375 degrees Celsius and a pressure of 725 millimeters of mercury, how many grams of ammonia can be produced? So let's write down what we know, and everything that we know is about water. So it says here you have the volume of water is going to be 5 liters. So it's actually steam if it's water and it's a gas. Anyhow, the temperature is 375 degrees Celsius. If I convert that into Kelvin, I add 273 and I get 648 K. Then the pressure is 725 millimeters of mercury. I'm just going to go ahead and convert that into atmospheres using the conversion factor of 1 atmosphere is equal to 760 millimeters of mercury, and I get 0.954 atmospheres. Okay, so I have the volume, temperature, and pressure, and that's all for steam or water, gas. Anyhow, I'm trying to figure out how many grams of ammonia. So what I'm trying to figure out is the mass of NH3, but I only have information about H2O gas. So from the ideal gas law, PV is equal to nRT. I have my temperature, I have my volume, I have my pressure. R is a constant, so I can figure out the number of moles of H2O. But if I have the number of moles of H2O, I can use the conversion factor from my balanced equation that for every 6 moles of water, I form 4 moles of ammonia. If I know the number of moles of ammonia, then I can just use the molar mass of ammonia, which is 17.03 grams per mole, to figure out the mass of ammonia. If you don't follow me, let's just move ahead and calculate the number of moles of H2O gas. So we're going to write down here the number of moles of H2O, and I'm going to put gas here just so we know what we're doing, is going to be equal to PV divided by RT. So let's put in the numbers. So our pressure is 0.954 atmospheres. Our volume is 5.00 liters. The gas constant is 0.0821 liters atmospheres per mole K, multiplied by my temperature, which is 648 Kelvin. So when I put all that in my calculator, I ended up with 0.0897 moles of steam, so water, gas, anyhow, H2O gas. Okay, but that just tells me the number of moles of water, but where I am now is I'm right here. I have the number of moles of water. So if I just use a simple conversion factor, I can say that for every 0.0897 moles, I'm just going to put H2O that I have. I know that for every 6 moles of H2O that's consumed in my reaction, I produce 4 moles of ammonia. So you can see that if I was to just stop my math here, moles of water would cancel out. I'd get the number of moles of ammonia, but that's not my ultimate goal. My ultimate goal is to figure out the number of grams of ammonia, but I do know that for every 1 mole of ammonia, I have 17.03 grams of ammonia. So there you go. You can see the moles of ammonia are going to cancel out. I am left over with grams of ammonia. And when I put that in my calculator, I get 1.02 grams of ammonia. So there's not a lot of complicated math in the problem. It's more about identifying when to use the ideal gas law and then how to use a little bit of stoichiometry from a balanced equation to get the number of grams of ammonia from the number of moles of water steam. So again, just like everything in chemistry, practice makes perfect, and I think it's a good idea for all chemistry students or anybody who's learning chemistry to commit the ideal gas law to memory. So PV equals nRT will get you a long ways when you're studying gases.